Let's talk about the median of a data set. So the median is a measure of the middle or center of a data series. However, it's not the same thing as the average, and so the relationship between them can be a little bit confusing. Let's look at our example data set here, and let's figure out what the median is. The median is the middle by count, and so in order to find it, we need to figure out how many data points there are, and then we need to separate them into two groups, a low group and a high group, on the basis of simple count so that there are equal numbers in each group. The easiest way to do this is to organize the data by sorting it. So we're going to take this data series here and we're going to sort it. I'm going to write down all these numbers in order and just rearrange the same numbers. So this is, in a sense, the same data series, but now sorted. So the median is the middle by count. There are 10 numbers in this data series, and so we want to find the middle by blocking that 10 into 5 and 5. And so we're going to cut it into two segments by dividing it right here between this 6 and this 8. So that's the median, except the median is supposed to be a number, not a purple line that I draw on the chalkboard in order to divide that 6 from that 8. And so this doesn't seem to give us a number here. How do we produce a number from this? Well, because we've drawn this line between the 6 and the 8, then we find the number right between the 6 and the 8, which obviously is 7. But if the numbers were more complicated, you would do something like this, and you would get that 7. So halfway between the 6 and the 8, we find that to be the median. So that's the median. And it has another name. We'll also call it Q2, which is a little bit of a mysterious name at this point. But that's another name for the median. So what's the purpose of the median? It finds the middle point, which usually is a typical value of the data. Usually it's an ordinary or normal value for the data. If these are children's ages, then the ages are around about 7 typically. The average age here is 6, which is different from the median, which is 7 in this example. The median is a dividing point which divides the data naturally into halves. If we want to furthermore subdivide the data into quarters, then we'll have to draw more dividing lines. Before we get to that, let's talk about what would happen if we had an odd number of data points here. So let's imagine that instead of having 110, we just had instead of having 2 10s, we just had 1. So we have 1, 2, 3, 3, 6. So this is a bit of a what if. What if the data looked like this? Then to divide it in half by count, we would have a slightly more complicated situation because there are 9 data points. So we have to recognize that there are 4 here and 4 here and 1 in the middle. And if there is 1 in the middle because the data set is odd by count, then we divide here and the median is exactly 6. So if you have an odd number of data points, the median will be that central data point after the data is sorted. If you have an even number of data points, then the median will be halfway in between the 2 data points which fall in the middle when the data is sorted. So this is how we divide the data into 2 halves. And there's a little bit of a finesse that has to happen whether the data is even or odd. What if we want to divide the data into quarters? Well, then basically we take the halves that we've created by dividing it by the median, and we cut those halves in half in order to furthermore subdivide. And so basically what we're doing here is we're taking the lower segment and finding the median of the lower segment. We're taking the upper segment and finding the median of the upper segment in order to further subdivide into quarters. Now you'll notice here that this lower segment is odd by count because there are 5. And because it is odd by count, when we divide it in half, we're actually finding a central value here, which is 3. So 3 is a dividing point which helps us divide the data into quarters, and so is 9. And they have their own names. They are Q1. Q1 is 3. And furthermore, Q3 is 9. So now you can see why the median is called Q2, because when we quarter the data by cutting it, we cut it 3 times. The cut positions are Q1, Q2, and Q3. And by those 3 cuts, Q1, Q2, and Q3, the data is evenly subdivided into equal portions, equal by count, and those portions are called the quartiles, or sometimes the term quartile refers to the cut positions themselves, the Q1, Q2, and Q3. And this word quarter or quartile is the reason why we use the letter Q here. Now, things are a little dicier depending on whether we have odd or even data sets. So if we have an odd data set by count, then the median itself is um, is one of the data points. And then when we refer to the lower half of the data or the upper half of the data, then we have to think about, are we including that median, 6 in this case, in the upper half or lower half? Is it part of both halves? Is it part of neither half? So we have to make some judgment calls there. The typical, actually, people make these judgment calls in different ways. The typical judgment call to make is if the original data set is odd and the median is one of the data points, then it is not part of either half. So the lower half is just these 4 data points, and the upper half is just these 4, and the median is excluded from both halves. So that when we are referring to the half and trying to further subdivide that, we're actually dividing it here between the 2 and the 3 to get the first quartile, and here between the 8 and the 9 to get the second quartile. Now, when we divide between 2 data points, then again, we have to do this trick of finding the number right between. So Q1 here is going to be the number right between 2 and 3, which is 2.5. And Q3 is going to be the number right between 8 and 9, which is 8.5. Now, I should caution you that these little fiddly details about whether we include or exclude on the basis of whether it's odd or even, and how we subdivide between 2 things, these are handled slightly differently by different systems. So you may see one spreadsheet program would do one thing, Python would do another thing. If you actually plug this data set, if you plug this data set into Python and ask it using pandas for the median, no, for the Q3 of this, I think it will actually tell you 8.75 because it has a kind of a clever and sophisticated way of dividing in such a way that it's trying to catch exactly 3/4 instead of half. So there's a little bit of sneakiness here, and I don't want you to trouble yourself with it. For our purposes, we're just going to take the middle point or right between the middle points, and then the median of the upper and lower sections will be the simplest approach for us. So this is how you calculate a median. Now, the median is the center of the data set by this count process. The mean of the data set is also an idea of the center of the data set, and it's also the sort of a notion of what is the typical data value. So the relationship between the mean and the median is kind of like they're both competing for attention. They're both trying to tell us what's the center of the data set. And so to talk about really what's the point of having 2 different measures of the center, I'd like to look at an example of a real data set, and that is the distances between the sun and the various planets. And let's calculate the mean and the median of that data set, and let's see how they relate to one another. So here are the 8 planets. Sorry, Pluto. And here are the distances of those planets from the sun. Now, these are average distances, and the units are in millions of miles because the distances are pretty far here. So you can see that here's Earth, 93 million miles on average from the sun. What you should notice about this data is that a lot of the values are fairly comparable to each other, but we've got a couple real outliers here. We've got a couple planets that are very, very, very far from the sun. Now, when we calculate the average distance from the sun, we get a bit of a surprise here. When we calculate the average distance, or mean, the average is 786. And that's 786 million miles from the sun. Now, the average is a lot like Saturn's orbit here, but it seems very high, especially considering that most of the planets are closer than that. However, when we calculate the median, or Q2, then what we do is we cut it in half by count. It's even, sorry, Pluto, because there are 8 planets only. And so we take these 2 values and we average these, and we get the value right in between, which is 313 million miles from the sun. So the median here is 313. Now, which of these is a better reflection of the typical distance of a planet from the sun in our solar system? Arguably, 313 is a better measurement of what is typical. Arguably, this average is kind of skewed or thrown off by the fact that Neptune is just so profoundly far away. Neptune itself contributes 2,800 to the sum when we add up all of these, And when we divide by 8, it's contributing more than 300 just to the answer here. So one data point, which is like really, really huge, is going to very much throw off the average, but it's not going to throw off the median very much. So if you want a typical, then median is often a better strategy than mean for trying to talk about what is typical. The same kind of thing happens with data sets that are very, very skewed because some of the data is way, way out there and the rest of it is sort of more centrally located. So American wealth levels, for example, if you try to calculate the average net worth of Americans, then you have some data points in there like Jeff Bezos, which contribute, $100 billion to that total before division by the number of Americans. And that one data point will throw off the average by, it works out to about $400. So if you calculate the median instead of the average, then Jeff Bezos counts as one. And so you get a value which is a better reflection of what is typical when we calculate the median instead of the mean.